Scotland. A land of imposing peaks and deep waters. For the country to stay connected, this unique environment poses huge obstacles. For project manager Lawrence Shackman, linking the nation is at the top of the agenda.
The Forth estuary divides Scotland into two halves. So from a transport point of view, it's a huge natural obstacle. 1890, the world-famous Forth Railway Bridge was built, and in 1964, the Forth Road Bridge was built to allow cars and heavy goods to cross.
But half a century later, traffic has more than doubled, and the road bridge is no longer up to the job.
A large degree of corrosion was found. Thousands of the individual strands were actually found to be broken. If the bridge continued to decay, it might need to close to all vehicles by 2021, bringing the central belt of Scotland to a standstill.
To keep the nation moving, a new bridge was urgently needed. So engineers have crafted a structure like no other on Earth. This is the Queensferry Crossing. A gigantic triple-towered cable-stay bridge, the largest on Earth.
This undoubtedly has stretched the limits of what we believe is possible. It's incredibly light, it's incredibly slender, and yet it is massive.
The Queensferry Crossing itself is an engineering icon which takes its place beside the other two great bridges.
It's a world beater. This is the longest two-span cable stay structure in the world. This really is engineering pushed to the limit.
Flying 55 metres over the water below, this £1.35 billion project stretches a whopping 2.7 kilometres from shore to shore. It's supported by 3 gigantic towers, reaching 210 metres high, the equivalent of 48 London buses stacked one on top of the other. The north and south towers sit atop record-breaking underwater concrete foundations, the largest reaching 50 metres deep, dwarfing the Statue of Liberty. And 122 deck pieces make up the 80,000-tonne roadway, secured by 37,000 kilometres of cable, enough to almost wrap around the planet. Hanging over the channel, this giant marks the dawn of a new age of superstructure.
So here we are inside the Queensferry Crossing, our 2.7 kilometre long solution to keep Scotland moving. It's an amazing place to come to and see such amazing technology and civil engineering skill come to reality.
But this beast of a bridge isn't only super long.
See you at the top.
Its 3 towers are the tallest of any bridge in the country. At 200 metres above the bedrock, the maintenance hoist reaches its limit. To reach further, Lawrence must climb to the concrete summit.
It's very rare for anyone to come up here, to be able to see out across to Fife, across to Edinburgh, over to the right there. It's absolutely stunning.
Soaring 210 metres over the landscape, the Queensferry Crossing's daring construction team reach extraordinary heights.
Being on a bridge that's so tall, so high up, the wind speeds are incredibly high at times. If you're building a bridge like this, you've got to have a really good head for heights. You've got to be fit, you've got to be able. And for the guys building this tower, they probably have one of the best offices in the world.
To construct a record-breaking piece of engineering, the team faced a list of seemingly impossible challenges. How do you erect enormous towers in a deep and formidable sea channel?
To build your structural foundations, you have to get down to deep depths, up to 40 metres deep.
And reinforce a slender bridge deck to stay strong and rigid across such a vast span.
There's heavy traffic that needs to be supported, and this creates huge sort of imbalances that really challenges the performance of the deck itself.
And where vehicles on the old bridge had no protection from high winds, how will the new crossing take on Mother Nature?
The wind speeds can get up to 120 miles an hour. That puts road users at risk.
This is the Queensferry Crossing. A record-breaking structure, the likes of which the world has never seen before. 35,000 tons of steel has gone into the bridge deck alone, the equivalent weight of 200 747 passenger liners. Every day, it carries 80,000 cars and heavy goods vehicles, keeping Scotland on the move 24/7. But creating a world-beating bridge like this is a seemingly impossible task. Before construction could begin, engineer Douglas Halliday and his team needed to create a solid foothold at the bottom of the sea.
Want to build your foundations is a major undertaking. This is a major channel, it's a major estuary, which creates all sorts of problems. You're talking 40 metres plus below water level to the bedrock. You only get one chance, really, to get that foundation installed.
Where deep water foundations are fundamental to the superstructure, the team had to take the plunge.
The south tower and the north tower foundations were constructed within caissons because of the depth. Twin-walled steel tubes, open-ended, top and bottom, and gradually we just tilted and shook that caisson down to bedrock level, constantly monitoring the position of the caisson using GPS techniques. It was critical that we got the position of the caisson correct within 250 millimetres of the design location. That was an immense achievement.
With the caissons placed with extreme precision, pumps completely emptied them of seawater. And in an unparalleled 15-day operation, running 24 hours a day, the team undertook the planet's longest ever continuous concrete pour below water level.
It's quite hard to appreciate the full magnitude of the scale of what's below the water here. So just to give you an idea, you've got roughly 50 metres of tower on display here. Below water, you've probably got another 40 metres before you hit the bedrock. So that's the sort of scale we're talking about below the water here. It is an amazing engineering achievement.
But for the central tower foundations, engineers saw an opportunity that they couldn't pass up.
This location was chosen because of the existence of a dolerite, very, very hard volcanic rocky outcrop in the middle of the Firth of Forth. So it was ideal to set the central tower foundation on because of the immense pressure that rock is going to take.
To prepare the super tough rock, the team blasted away roughly 5,000 cubic metres of material with powerful explosives and shaped it to hold 4,000 cubic metres of concrete.
So there's a robust reinforced concrete base below that tower on which we've placed some decorative rock effectively to try and create the illusion that the tower is coming straight out of the rock.
Have you got a souvenir piece?
All civil engineers keep a piece of rock.
With a rock-solid foundation in place, teams set to work erecting the country's 3 tallest ever bridge towers. In another remarkable feat, 24,000 cubic metres of concrete was poured in incremental stages. pumped all the way from barges at water level to 210 metres high. And after almost 2 years of perseverance through the Scottish weather, the towers topped out and were finally ready to support a roadway. But to reach them from the shore, engineer Jill Baker and the team faced another obstacle.
There were many challenges to constructing both the north and the south approach viaducts, and this very steep sloping ground made it very unsuitable for heavy craneage. You need a good, secure, stable, level base for any use of craneage. So we had to find a different solution for the approach viaducts.
To link the steep banks to the towers would require the team to draw inspiration from the pioneers of the past. At a South Yorkshire limestone quarry in the UK. Engineer Luke Bisbee is on the hunt for an innovation that changed the course of history.
During World War II, Hitler ordered his troops to start destroying bridges. And this was a very clever idea to slow down the Allied forces. No bridge means the Allied forces have a massive detour in order to get where they're going.
To fight back, the Allies needed to rebuild bridges, and fast. One solution was to pre-assemble temporary bridge parts. But the army had no easy access to cranes to lift heavy components into place. Giant deck spans could be built extra long to balance the load and then swung out from the bank. But the longer construction wasted valuable time in the hunt for the enemy. A portable pyramid bridge might have done the job. But with 40-ton tanks needing to cross, these spans just wouldn't hold up, leaving the military high and dry. Knowing that bridges were vital to the war effort, British engineer Sir Donald Bailey started sketching up an idea on the back of an envelope. In 1940, he developed a concept that changed the war. This is a Bailey Bridge.
Wow, so this is the modern version of the Bailey Bridge. A portable, quick-to-build bridge that can be adapted to suit just about any location. And this one here is spanning 42 meters from side to side over a drop of about 20 meters. Pretty spectacular.
Over 80 years after its conception, Bailey's flat-packed bridge design is being erected to connect two important areas of this quarry, without the assistance of heavy lifting cranes.
So you can see here, this is one panel section of the bridge from here over to there. By adding more panels along the bridge, you can adapt this for your particular location. No single piece weighed more than 570 pounds. And this meant that any piece could be lifted by 6 soldiers, which crucially meant that no cranes or heavy lifting was required, which is absolutely critical in a combat situation.
Super light bridge sections could be easily transported to the battlefield and assembled by hand. And its modular design meant that the Bailey Bridge could be progressively launched, growing as it inches forward.
Okay, boys, pull the spikes.
But how were Bailey bridges built across rivers and ravines without a crane?
Nice and slowly, if you please.
By counterweighting one end of the lightweight structure, it could be pushed out and over the valley.
The key thing about the Bailey Bridge is that you can launch it from one side. That is absolutely extraordinary. 104 tons of bridge just sliding past me on some rollers. Unbelievable.
But without supports to hold up the span, there's an additional challenge to overcome.
A key problem that you have is that the front of the bridge is going to want to angle down under the weight of the structure. And so it's really important when you're launching a bridge in this way to keep the nose of the bridge up, because otherwise, as you're pushing it across, you might just bump into the other side.
But Bailey had thought of everything and angled the front section of his bridge up to ensure it cleared the bank on the other side.
Here it comes. I think this is actually a pretty critical moment right here. So they've made it here to the other side. They've actually done it.
Okay, spikes in, boys.
Really an extraordinary thing to see.
By the end of the war, around 700,000 Bailey Bridge panels had been made, enough to stretch from London to St. Petersburg. Both British and American generals have sung the praises of the Bailey Bridge as one of the key factors that helped the Allies win the war.
With his ingenious yet simple design for a bridge that could be built and launched by hand and without a crane, Donald Bailey had helped bring an end to World War II. This is an amazing thing. To see this technology still doing its job so many years later is really wonderful and a real testament to the innovation that was involved.
In Scotland, engineers have taken the same concept and supersized it. The only way to the Queensferry Crossing's towers from the shore is with gigantic, progressively launched approach viaducts.
The chosen solution for the South Approach Viaduct was a progressive launch. It was launched span by span. We achieved this launch, which goes out virtually half a kilometre to where the cable stay bridge is. This eliminated the need for any large cranes.
Where heavy lifting cranes can't be erected on the steep slopes, 6 concrete piers were evenly arranged out towards the towers. The team then inched the bridge deck forward from the abutment piece by piece. Each time they reached a pier, a new section was welded to the back. And the process would repeat until the viaduct reached half a kilometre out over the supporting piers. And just like with the Bailey Bridge, the overhanging deck had to fight gravity.
As the launch progressed, the tip would want to deflect under its own weight. This could have been catastrophe if the tip actually put lateral load into these piers. But we had this king post system in place, a 35-metre vertical temporary post. There was a strand system coming over the king post and connected to the tip. As these strands were tensioned, it would lift the tip and land it on the pier. And it was a pretty remarkable solution.
But where the North Shore's slopes are even steeper, a more extreme approach was needed.
We would have had to excavate a lot more ground to assemble the girders at the right profile for the launch. So the solution here, rather than being a progressive launch, the whole structure, 220 metres, was assembled as one unit, and then it was launched in one massive launch.
In a single daring manoeuvre, engineers pushed the enormous deck span directly forward, and then pivoted over the supporting pier to tilt upwards and align with the rest of the bridge structure.
It was a big relief when we finally achieved our desired solution. I don't know of another launch so large, 6,000 tonnes, being pushed out 220 metres and then having to do this pivot. It was remarkable engineering, super bold, and it's the best of British engineering.
In Scotland is a superstructure that defies the impossible. In a bid to keep the country connected, the triple-towered Queensferry Crossing boasts 2 enormous 650-metre spans. Over 2,500 concrete pours executed across the project pumped a staggering 150,000 tonnes of concrete into the megastructure. But before vehicles can cross the channel, they're going to need a road to drive on. Engineer Richard Hornby oversaw the crucial deck segment construction.
This is Rosyth Port here. It was the sort of the marine nerve centre for the project. For the deck itself, the steel was made in China. The units were delivered on 4 ships on this quayside here.
122 steel deck sections, each weighing up to 400 tonnes, were offloaded by a 1,000-tonne mega crane and taken one by one to the concrete casting shed to be capped by another 300 tonnes of reinforced concrete. But to get these super heavy deck pieces from the dockyard up onto the megastructure would be a battle with the elements.
The conditions on the east coast of Scotland are not benign. There's long periods of strong wind, there is a strong tidal flow. The sort of equipment that you need are very special pieces of equipment. Big floating crane that are stable in essentially open water.
But where the water depth varies, a one-size-fits-all solution just won't do.
The floating cranes need significant depths of water, and towards the ends of the bridge there really isn't enough water depth, and so you might well have had to have 2 different lifting systems, one using the floating crane and one to deal with the areas where the floating crane couldn't get to.
In a varied seascape where multiple systems would be needed, the practicality of floating cranes has to be ruled out. The team must find another way to install heavy deck segments by turning to history's innovators. In the rugged landscape of Lethbridge, Alberta.
Watch your step.
Mechanical engineer Agnes d'Entremont is exploring the deep ravines that kept southern Canada divided.
Connections by rail within southwestern Canada were really important at the end of the 19th century to get southern Alberta coal into British Columbia. But they had to deal with terrain like this, deep ravines. A real solution was needed for the railways to cross these dangerous river valleys.
Tasked with making this dream a reality was Assistant Chief of Engineering at Canadian Pacific Railway, John Edward Schwitzer. In 1909, he unveiled a revolutionary structure that changed the world of bridge engineering. The Lethbridge Viaduct.
Wow, it's incredible!
Over 1,600 metres long and 96 metres high, it's the longest and highest steel railway trestle in the world.
So this is it. This is Schwitzer's solution to keeping southwest Canada connected. The Lethbridge Viaduct, which you can see above me, spans this entire valley but keeps the rails almost level. But even more incredible was the technology and engineering they used to build it.
This enormous, world-beating piece of infrastructure,
Wow, it's so high.
was dubbed by many newspapers of the day as one of the wonders of the world.
At this point, the bridge is nearly 100 meters above us. Imagine having to lift massive steel beams that high in the air to construct this bridge. Having a crane down here would be impractical, not only because the terrain is rugged and there's a river, there are varying land heights, which would require multiple crane variations.
Just like in Scotland, the varied landscape meant that a single crane system wasn't enough.
So instead of putting the crane down here, Switzer put it up there.
In a stroke of genius, Schwitzer's cunning solution was to use a deck-mounted erection traveller crane. An enormous mobile gantry that travelled along the track atop the bridge. The original crane is no more, but Agnes is inspecting a scaled-down model.
It doesn't really look much like a crane. It looks more like a house on wheels. The giant shed at the back housed not only the engines to move the crane along the tracks, but also 6 hoisting engines that operated the jib arm. This is such a cool piece of engineering. You don't really see anything like this anymore.
Standing almost 20 metres tall, the 322-tonne erection traveller crane rode on the external walls of the bridge, allowing wagons to travel on the rails underneath the engine room to deliver materials to the boom at the front. And with 17 kilometres of cabling swinging components into place, the erection traveller built its own platform to migrate onto as the bridge deck grew. Only with the help of this remarkable machine.
What an amazing view from up here.
Was the construction of the world's longest steel trestle possible?
The workers who built this bridge must have had nerves of steel to have such a monster directly above them. This massive device where fully loaded rail cars could run underneath it, roaring with the sound of steam engines.
By shifting forward one piece at a time, it took 10 months to reach the West Bank. And as construction neared completion, workers leapt off the deck to be the first ones to the other side, much to the dismay of the foreman. A century later, the Lethbridge Viaduct still carries enormous trains weighing thousands of tons.
Without the erection traveller crane, this viaduct and the robust connection between Alberta and British Columbia wouldn't exist. What a remarkable piece of engineering.
Over 100 years since Schwitzer's inspired idea, Scotland's engineers have created a system that he could only have dreamed of. Not with 1, but 6 erection traveller cranes, or in this case, gantries, lifting 700-tonne deck units from floating barges and progressing forward as the structure grew. Breaking another world record, the central tower became the biggest balanced cantilever that ever existed, until the giant balancing act was sealed together to become a secured superstructure. Whose engineering secrets are now only found deep within.
This is a joint between 2 segments. This is the front edge of the already erected deck. The front foot of the gantry needed to be stressed down to all of this stiffening here, ready to lift up the 700 tons in front of it. The segment would have been drawn together, and then if we look up here, we can see that there's a metre wide strip of concrete that gets cast between the 2 segments and joins the 2 segments together.
With a cutting-edge iteration of the erection traveller crane, engineers have created an engineering masterpiece.
The lifting of these 700-tonne segments with lifting gantries was a hugely innovative piece of construction engineering, a development actually of lifting gantry technology that has been around for a century.
The Queensferry Crossing is the longest structure of its type ever built, and a lifeline to a nation. To keep its enormous 2.7-kilometre roadway up in the air requires a colossal cable stay system. But this extremely slender bridge hangs delicately over the sea, and a conventional cable arrangement just won't hold it.
As you see, it's a very elegant, slender structure. But if there was a traffic jam and all the traffic backed up, there would be all this weight on one side and none on the other, and the deck on the other span would lift up, and the deck on the loaded span would go down.
Where traditional cable stays would terminate before mid-span, an excessive load on one end of the bridge causes the slender deck to deflect, and the downward force would pull the cables in tension, lifting the opposite side. This long, slender deck profile needs additional support to stay standing.
If you don't provide that stiffness, the structure cannot resist the load on one side and would fall down under these asymmetric loadings.
To find a way to stiffen the bridge deck, inspiration might be found with the innovators of the past. Straddling the border between France and Spain are over 400 kilometers of steep precipices and deep ravines.
Marvelous journey. So beautiful.
On the French side of the Pyrenees mountain range, civil engineer Claude Lecaire is hunting down a relic from the golden age of locomotive travel.
In the early 20th century, the most efficient way to connect this region was by rail. To cross the Tete River, the gorge was very deep, and a stone bridge would have taken a lot of time, a lot of money. The suspension bridge is also a marvelous structure, but is not appropriate for railway. The train is a very heavy load, and when the train enters the bridge, it creates a huge deflection of the structure.
For a suspension bridge to cope with heavy trains, it was going to need special reinforcement. But in 1900, French military engineer Albert Giscard patented a clever system that enabled him to build a bridge like none that had ever come before.
I can see it now. It's just after this curve. You will see it's a very marvelous structure.
This is the Pont Giscard.
And there we are.
A cable-supported railway crossing.
It's not a standard suspension bridge. Look at the cross cable. There, in the middle of the structure. It's so impressive. It's a really elegant structure. It's something very clever.
Hanging 80 meters over the valley below, it's the oldest cross-cable railway suspension bridge in existence.
Oh wow, what a great view from here. It's impossible to see it when you are in the train, but from this point of view, you can see the fantastic and clever cable arrangement. It's something very, very special. There is no single suspension cable. There is two suspensions that cross in the middle of the bridge, and that makes all the suspension system very stiff.
Weighing only 873 tons, this seemingly fragile structure stands strong after 110 years. thanks to Gisclar's ingenious reinforcement concept. A traditional suspension bridge sports a pair of cables strung across the supporting towers and vertical wires that hold up the deck. But when a heavy load like a train enters or leaves one side of the bridge, the imbalanced heavy weight could cause disastrous deflections in the deck, pulling the structure in the wrong direction. Gisclar solved this by continuing the cables from each tower across to the base of the opposite side, crossing them in the middle. Now the heavy load is shared across the intersecting cables to both solid ground abutments. And with the complex web of cables creating triangular truss-like geometries, even more stiffness has been introduced into the deck.
Here comes the train. As the train enters the bridge, the heavy gravity load on that side is supported by both sides and both pylons. Gisclar's idea was really brilliant. It's a very innovative idea.
It took construction teams 3 years of high-altitude labour to build this super-strong bridge with its intricate overlapping cable configuration. Until finally the 253-metre-long crossing opened in 1910 as the first of its type ever built. Although many had attempted traditional suspension bridges for railways, none had the strength and stiffness to stand the test of time quite like the Pont Gisclar.
So Gisclar built roughly 20 bridges of this type, but this is the only one for railway. This bridge is a really great design. It's an inspiration for engineers today.
In Scotland, engineers have built a cross-cable system, and on a colossal scale. Enhancing structural strength and depth to a super long, super slender deck profile.
Here is midspan. So if we look up there, the height of where those cables intersect at their very highest is the apparent depth of structure. If you have load on one span, these stays here will be delivering this load here, and these stays coming down from the north tower will actually act to transfer load from the far span all the way back to terra firma.
Where the conventional cable stay method would have failed, the team opted to extend their cable stays further, crossing at mid-span, allowing the force of uneven weight loading to be transferred all the way across the intersecting cables to the opposite abutment.
Introduction of additional stiffness through an overlapping stay system. This is the first time it's been done on a cable stay bridge of this scale.
At 420 metres, these cables are some of the longest in the world. And should they ever need any repairs,
What's your step?
the team have a remarkable system in place.
Yeah, here's a good view of a cable anchorage. So you can actually just see the strands disappearing through a hole in the deck, and each of those strands is individually anchored so that you can take one out and remove it.
Inside each cable are between 50 and 100 strands of woven wire, which from under the deck can each be pulled out and re-threaded without disrupting the other strands in the cable.
The replacement of individual cables with minimum disruption to traffic was a fundamental requirement. Traffic could keep moving, but you can also return to the position as new when you replace the cable.
With this unique system in place, the Queensferry Crossing is the longest cross-cable stayed bridge anywhere on Earth. But even with this enormous superstructure erected, the team must still take on Mother Nature. Engineer Ian Murray oversees ongoing bridge operations.
As you can see from the site, it's a very open environment. We're very close to the sea and very exposed to the wind. The wind speeds can get up to 120 miles an hour. On the bridge, these high rectangular vehicles, they just act like a sail and they have the same impact as the wind has on a yacht.
On the old road bridge, gale force winds had such power that the structure could violently ripple and swell. And the ferocious gusts could even tip over high-sided trucks. For the safety of drivers and residents living on the banks below, bridge closures were essential. But the engineers of the Queensferry Crossing have got it covered.
So the solution we came up with was a 6 louvre wind barrier, which basically deflects the wind over the top of the road and protects the vehicles from the wind. The bottom 2 louvres are this way round, which allows the wind to come in and start to fade over the top. As you go up, higher up, then the wind is helped to go over the traffic. It's fantastic because it's allowing the traffic to move uninterrupted at all times of the year. Since the bridge opened, over that period, if we were still on the Forth Road Bridge, the bridge would have been shut 86 times to traffic. It's a genius solution to allow the traffic to keep moving. It's just a phenomenal piece of engineering.
For the team behind this daring project, the engineering achievement is immeasurable.
It's an incredible feeling knowing that you're part of one of the key pieces of infrastructure in the UK. Really, there are none like the Queensferry Crossing in terms of its scale and significance.
By building on the work of the pioneers of the past, overcoming huge challenges, and pushing the boundaries of innovation.
I think if you're a civil engineer and a project like this doesn't excite you, you're probably in the wrong game. It is a groundbreaking project. It's just an immense engineering achievement.
Engineers have succeeded in making the impossible possible.
There was a lot of challenging days out there. We worked 24 hours a day. The outcome is a phenomenal bridge and it's recognised across the world. There's no doubt the Queensferry Crossing provides a lifeline for Scotland.